Hi friends, welcome back to our channel Physics Tutorial. Today we are going to discuss the second part of electrostatic potential and capacitance. So in the last class we had discussed potential due to a point charge, potential due to an electric dipole, etc. Right, now we are going to discuss about the potential due to system of charges. Are you ready? Now we can move to the video. Here we are going to find the potential due to a system of charges. So here we can see this a point P, and there are a system of charges distributed over here, that is Q1, Q2, Q3, Q4, Q5, like that. And the position vectors of these charges are R1P, R2P, R3P, R4P, R5P, etc. Okay, so like that n number of charges we can consider here, and here we are finding the electric potential at P due to all these charges. So how we can find the electric potential at P due to all these charges, that means Q1, Q2, Q3, Q4, etc. Qn. Okay, so in the case of electric field we have found such a system, right? So in the case of a system of charges, how we calculated the electric field? It was the algebraic sum of the fields due to each charge, right? Individual charges. So here also we have to do the same procedure. So first of all we will calculate the electric potential due to charge Q1, okay, at P. So what will be the equation for electric potential at P due to Q1? So how we can find that V1 will be equal to 1 by 4 pi epsilon 0 Q1 by R1P, right? So here R1P is the distance between Q1 and P. And now in a similar way we have to find V2, V3, V4, etc. Vn, right? So next equation also we can write. How we can write V2? V2 is the potential at P due to charge Q2. So how we can write? 1 by 4 pi epsilon 0 Q2 by R2P, right? So how we can find the total potential? So here V1, V2 are the potentials due to Q1 and Q2 charges, right? So we can find all the charges and then we can add it. That means V will be equal to V1 plus V2 plus V3 plus etc. plus Vn. That means, so the potential at P due to the total charge will be the algebraic sum of the potentials due to individual charges. So here we have to find the potential due to individual charges, then we can take the algebraic sum. That means we can add it together. So like that we will find here, that is V is equal to V1 plus V2 plus etc. plus Vn. So if we substitute the equations of V1, V2, how we will get the equation? V will be equal to, instead of V1 we can give 1 by 4 pi epsilon 0 Q1 by R1P plus V2 means 1 by 4 pi epsilon 0 Q2 by R2P plus etc. plus 1 by 4 pi epsilon 0 Qn by Rnp we can write. Okay, so if we take the constants outside, what we will get? V will be equal to 1 by 4 pi epsilon 0 Q1 by R1P plus Q2 by R2P plus etc. plus Qn by Rnp. So that means the potential due to the total charge will be the algebraic sum of the potentials due to individual charges. That is the potential due to a system of charges. Clear? We have to study equipotential surfaces. Eq means that will be equal, right? So we can understand from the name itself that will be having equal potential on all the surfaces. Okay, so equipotential surface is a surface with a constant value of potential at all points on the surface. So if you are taking an equipotential surface, the value of potential will be same at all points. Okay, so that is equipotential surfaces. That means an equipotential surface is a surface with a constant value of potential at all points on the surface. അതായത് ഒരു equipotential surfaceന്റെ കേസിൽ എന്താണ്, സർഫസ് എടുത്താൽ അവിടെ ഉണ്ടാവുന്ന ഓരോ പോയിന്റിലും പൊട്ടൻഷ്യൽ എന്തായിരിക്കും, സെയിം ആയിരിക്കും. ഓക്കെ, അതാണ് equipotential surface. So what will be the cases of equipotential surface? അതായത് ഒരു equipotential surface എടുത്തു കഴിഞ്ഞാൽ there will be no potential difference between any two points on the equipotential surface, because all the potentials are same, means there will be no potential difference between any two points on the equipotential surface. So no work is required to move a test charge on the surface. That means if we are taking any 2 points on the same surface, that means if they are equipotential, the potential will be the same. So it is not necessary to do any work to move a test charge from one point to another. Okay. Then another thing is that for any charge configuration, suppose it is negative or positive, equipotential surface through a point is normal to the electric field at that point. So this equipotential surface will be normal to the electric field. So these 2 points about the equipotential surface you should remember. First one is there is no potential difference between any 2 points. So no work is required to move a test charge on the surface. And the second thing is for any charge configuration, the equipotential surface through a point is normal to the electric field at that point. And here we can see that for a single charge, because if you are taking a single point charge, the equipotential surface we can find by using the equation V will be equal to 1 by 4 pi epsilon 0 Q by R. So here we can see this V will be the same for a equipotential surface. Here we can see that. Okay. Here we can see this is the case of a point charge plus Q charge we are taking here, and we can see the equipotential surface. So here if you are taking any point on the surface, each point will be having the same potential. So like that we will get the concentric circles for a point charge. Okay. And in the case of uniform electric field, we are taking like this. Here we can see the uniform electric field. This will be the case of an equipotential surface. And for a dipole, so these diagrams are there in your textbook, that is page number 54. Then you can easily understand the difference between these. So just understand the diagram. Okay. And now for a dipole means there will be 2 charges, right? Positive and negative charges are there. So this will be attract. If you are taking 2 identical points, that means identical charges plus Q. Suppose here we are taking plus Q charge and this is also plus Q charge. So what happens is that this will be repelled, right? So similar charges, they will repel each other, and here we can see more concentration in this side. Okay. So this will be the case of a 2 positive charges. Okay. All these are about this equipotential surface. Now we are going to derive the relation between field and potential, electric field and electric potential. So for that we can consider 2 points, that is A and B. Here we can see that a charge plus Q is kept here, and these 2 points, that is A and B, are separated by a small distance dx. So dx is very small distance, therefore these 2 points, that is A and B, are said to be very close, right? And the potential at A is taken as V plus dV and potential at B is V. Clear? Now what will be the direction of electric field in this case? Here we are taking the positive charge, plus Q charge is kept here. So in which direction we will get the electric field? So this is positive, means this will be, yes, away from this. Okay, so the direction of electric field is here like this, that will be against this dx. Okay, and now we can move a unit positive charge through this distance, right? For moving a unit positive charge from A to B, what we have to do? Because here we know that this electric field is in this direction and dx is in the opposite direction, right? So we have to do a work against the field, right? So what will be the work done? Work done, how we will calculate? Work done is force into displacement, right? So dW we can take, because only a small work we have to do, because this is very close. A and B are very close to each other. That means we have to do a small work for moving a unit charge between them. Okay, so here we are getting dW as the small work done. Then how we can find force? Sorry, work done. Work done is force into displacement, right? So here force is F into displacement means dx. Dx is the distance between these 2 points, right? And now F into dx is work done, and we can relate it with the electric field, right? Because here we have to find the relation between field and potential. So in terms of electric field, we can write the equation of force. Here we know that E is equal to F by Q. Electric field will be equal to force by charge. Clear? Now how we can find F? F will be equal to E into Q, right? So here we have unit positive charge. So this Q will be 1. So we can replace this F with E. Clear? So E will be equal to F. Then what will be the equation? Here dW is equal to F dot dx. That will be equal to, here instead of F we can write E dot dx, and now we know that this electric field and dx both are in opposite direction, means the angle will be 180 degree, right? So what will be cos 180? Cos 180 is equal to, yes, cos 180 minus 1, right? So that will be minus E dx. Clear? Because here this E and dx are opposite directions, so that angle will be 180 degree. Then cos 180 E dx means E dot dx means E dx cos 180, right? So that will be minus E dx. Clear? So that is the first equation. And now we can find the potential difference between these 2 points. How we can find the potential difference? That is the work done to move plus 1 coulomb charge, right? That will be equal to potential difference dV. So work done to move plus 1 coulomb charge in between the 2 points is potential difference dV. So how work done, potential difference means that work done we have to calculate. So W will be equal to dV. Work done to move plus 1 coulomb charge will be equal to potential difference, means W is equal to dV. So for unit charge we can write it. Otherwise W will be equal to Q into dV. Right. So here Q is equal to 1. Therefore W is equal to dV. So this is the second equation. Now we can compare these two equations 1 and 2. So LHS is same, right? dW is the LHS. So how we can write this? Yes, we can equate the two equations. So dV will be equal to minus E dx. Both the RHS are same. So dV is equal to minus E dx means E will be equal to minus dV by dx. So this is the relation connecting field and potential. Here we can see E is equal to minus dV by dx. Suppose if you are writing this dV by dt means that we will say as rate of change of, right? Here we have minus dV by dx. If it is coming like dx, we will say that this is the gradient of, okay. So how we can define this? This will be electric field intensity, that is equal to the negative gradient of potential, right? That is electric field intensity is equal to the negative gradient of potential difference, that is E is equal to minus dV by dx. That is the relation connecting this field and potential. And for calculations and all, we will use this relation E is equal to V by L. So usually we will use this equation E is equal to V by L. So understand this also. You have to remember E is equal to V by L for calculations, and this is the relation that we are getting from field and potential. Clear? So that means the electric field intensity is the negative gradient of potential difference. Clear? Now we have potential energy of a system of charges. So what is potential energy? Potential energy we have already studied, right? Energy means here we have to calculate the work done, right? Whenever we want to calculate energy, energy is actually the capacity for doing work, right? So we have to calculate the work done. And in the case of potential energy of a system of charges, here potential energy is the total amount of work done to bring the charges from infinity to their present positions. Suppose we are having two charges Q1 and Q2. Now we have to calculate the potential energy. Suppose there are two charges Q1 and Q2. Okay, so here this is a system of charges, and here we want to find the potential energy of this system of charges. Then what we can do? Potential energy is actually the work done. So the work done to bring these two charges from infinity to their present positions, that we have to find. So first of all we will calculate, suppose this is the infinity, and from infinity to this Q1 we have to bring this charge Q1, right? So for that the work done we have to calculate. Suppose it is W1, and in the same way we will find the work done to bring this charge Q2 from infinity to Q2 to its position, right? So we will get W2. So the total work W1 plus W2, that means if n number of charges are there, we will bring each charge from infinity to their present position, and that work done we will calculate, and that total work done will be equal to the potential energy. So that is actually the potential energy of a system of charges. We can consider one charge, two charge, three charge system like that. Okay, so we will discuss how to find the potential energy of a system of charges. So here that idea should be there, because that charges we have to bring from infinity to their present position, and the corresponding work we will add together. So to suppose there are three charges, what we have to do, we will bring each charges separately and we will add it together. And one more thing we have to understand is that here if we are finding that V, that is potential energy, so we can use the equation V is equal to W by Q, that is electric potential is equal to work done by charge. So how we can find work done? So W will be equal to V into Q, that means potential difference into charge. So that equation we will use throughout for this derivation, that means for finding potential energy of a system of charges. So all these two things you have to understand. That means what is potential energy? That is the total amount of work done to bring the charges from infinity to their present positions, and we are using the equation V is equal to W by Q, and W will be equal to V into Q. So this you have to keep in your mind, and now we can find the potential energy of system of charges. Here we can consider two charges. Here we can see that, right? Here Q1 is there and this is Q2, and they are separated by a distance R12, right? This point is A and this point is B. Now we have to find the potential energy of this system. That means here how we can find the total potential energy? Here there are two charges, so first of all we have to bring this Q1 charge from infinity to this point A. Then how we can find the work done? Here that work done W will be equal to V into Q, right? So what is Q here? Here only one charge is there, that means Q1 only is there, and then is there any other charges acting here? No. So only Q1 is there, means here the work done will be 0. So W will be equal to V into Q, because there is no other charges acting on this Q1. So that total work done W1 will be equal to 0 here. And now we have to bring the charge Q2 from infinity to B. So for that we have to do the work, and that work we have to calculate. So how we can find the work done? W will be equal to V into Q, that equation we can use. And if you consider Q2, is there any other charges acting on this system? Because this is a system of charges, and here Q1 is also there. So this Q1 will be producing a electric potential on Q2. So Q1 will make a electric potential. So that also we have to find. So Q2 means here V1 into that charge Q2 we have to find, right? W will be equal to V1 into Q2. That V1 is the electric potential at B due to charge Q1. Clear? Because there is two charges at the same time here. So if we were bringing Q1, only Q1 was there. That is why the total work done was 0. And in the case of Q2, here already Q1 is there, and into that system we are bringing this Q2, right? So this Q1 will make an potential on Q2. So that value we have to find. So V1 will be equal to 1 by 4 pi epsilon 0 Q1 by R12. Clear? So due to this Q1 charge, the potential is produced here. So Q1 by R12 is there. Now we can find the work done. How we can find work done? W is equal to V into Q. That V means V1 minus V infinity. Right, here only V1 is there into Q. So charge is Q2. So what will come? W will be equal to V1 into Q2. Then here V infinity was 0, right, because the first work done was 0. Then how we can write? V1 value we have already found, right? V1 is equal to 1 by 4 pi epsilon 0 Q1 by R12 into Q2. So the equation will be 1 by 4 pi epsilon 0 Q1 Q2 divided by R12, because this V1 into Q2 we are doing. So V1 is 1 by 4 pi epsilon 0 Q1 by R12 into Q2. So the this work done will be stored as the potential energy of the two particle system. So here we have U12 that is equal to 1 by 4 pi epsilon 0 Q1 Q2 by R12. So for finding the potential energy of any system of charges, we have to bring each charge from infinity to this field. Okay, so for that we have to do work. So that work we will find separately and we have to add it. So that work will be stored as the potential energy of the system. Clear? So like that we will find the potential energy of a system. So in the case of two particle system, here two charge system, here we will have the equation of potential energy as 1 by 4 pi epsilon 0 Q1 Q2 by R12. In similar way we can find the potential energy of a three charge system. Okay, so there will be three charges and now we can derive that equation. It is very easy to understand. If we understand the concept, it is easy to find the potential energy of three particle system also. Clear? Now we have to consider a three charge system. Here we are going to find the potential energy of system of charges and we are considering three charges, and you should understand that this is in the case of absence of external field, because here there is no external field acting on the system. Okay, now we can find the equation for potential energy. Here we are considering three charges, that is Q1, Q2 and the third charge anywhere we can keep. So here I just kept this Q3 and we name it as A, B and C. This is in the form of a triangle. It doesn't matter, at any shape we can give this. Okay. And the distance between these two charges Q1 and Q2 is R12, between Q1 and Q3 is R13 and the distance between Q2 and Q3 is R23. Here we have to find the potential energy. So how we can find? First of all we have to bring the charge Q1, then Q2, then Q3 from infinity to the present system. Okay, so for that we can consider the charge Q1. If we bring this Q1 charge, what will be the work done? Because we are bringing it from infinity to charge means infinity to A. So here there will be no work done, that we have already discussed in the last case, right? In two charge system we have already told. So there is no other charges, means the work done will be 0. So W1 is equal to 0. Then now we have to bring Q2 charge from infinity to B. So how we will find? Work done will be equal to W is equal to V into Q, that equation we are using here. So here B is there and into Q2, that the charge is Q2. So what is VB? VB means if we consider Q2, Q1 charge is already there, right? So due to this Q1 charge there will be a potential. So that we are finding here, that will be equal to 1 by 4 pi epsilon 0 Q1 divided by R12. So into Q2 means that work done we will get. So W2 is equal to 1 by 4 pi epsilon 0 Q1 Q2 by R12. Now that we have already told, that's why I am not giving that much explanation. And now we can bring charge Q3 from infinity to point C. So how we will bring Q3? So the equation for work done is W3 is equal to VC into Q3. And here VC means we can consider this charge Q3. Here already these two charges are there, Q1 and Q2 are there. So due to this Q1 and Q2 the potential will be there. So both we have to find here, right? So what will be the value of VC? Means equation of VC. That means first of all we have to find the potential due to this charge Q1, then potential due to charge Q2. Then how we can write? VC will be equal to 1 by 4 pi epsilon 0 Q1 by R13, because the distance between this Q1 and Q3 is R13, plus the distance between Q2 and Q3 is R23 and the charge is Q2. So 1 by 4 pi epsilon 0 Q2 by R23 is there. What will be the total work? Now we have to multiply with Q3, right? That means W3 is equal to VC into Q3. This is VC only. Now into Q3, that means 1 by 4 pi epsilon 0 Q1 Q3 by R13 plus 1 by 4 pi epsilon 0 Q2 Q3 by R23. So this is the work done to bring charge Q3 from infinity to C. Now we have to find the total work done. So that total work done will be stored as the potential energy. So how we can find total energy? That means W1 plus W2 plus W3, that is the total work. Then we can just add these three equations. So we can consider the first case it is 0, right? In second case these two equations are here. What is the equation? 1 by 4 pi epsilon 0. Yes, q1 q2 by r12 is there, and then 1 by 4 pi epsilon 0 q1 q3 by r13, 1 by 4 pi epsilon 0 q2 q3 by r23. Clear? So 1 by 4 pi epsilon 0 is common. So we can take it outside. Then inside the bracket q1 q2 by r12 plus q1 q3 by r13. These things will come here. So q1 q2 by r12, q1 q3 by r13 plus q2 q3 by r23. So that will be stored as the total potential energy of the system. So this is the potential energy of a 3 charge system, that is 1 by 4 pi epsilon 0 q1 q2 by r12 plus q1 q3 by r13 plus q2 q3 by r23. So this is the equation, and similar way we can find the total potential energy of 4 particle or 5 charge system, like that. So any number of charges are there means we have to find the work done for bringing all the charges, and we can add it to get the potential energy. Clear? Now hope it is clear to you. Now we can conclude the video. So the rest of the portion we can discuss in the next class. So thanks for watching.